Today's video is on atomic size and how we can tell that size based on the periodic table. So you're going to need your periodic tables for this video and a piece of paper for some notes. So if you need to, pause the video and then push play again when you've got a periodic table. So I'm going to start this with a couple of questions to see if you can figure them out. So the first question I'm going to ask you is for the atoms, which is bigger? And by bigger, I mean bigger in diameter. So for hydrogen and helium, the first two elements on the periodic table, which is bigger? So make a decision, write it down. Did you say hydrogen? Did you say helium? Which do you think is bigger? Well, let's look at the periodic table. I see hydrogen. It's number 1. It has a mass of 1. It's got 1 proton and 1 electron. Helium has a mass of 4. It has 2 protons, 2 neutrons, and 2 electrons. So that seems like a pretty obvious question. Helium is bigger. Well, that certainly would answer the question, which is bigger, if I said which is bigger in mass. But that's not how we determine the size of an atom. So how do we determine the size of the atom? Well, the size of the atom is based more on the electrons because it is the diameter or the size of the outermost orbital. So what is the diameter of the electron orbital? Sometimes they also talk about the radius, the atomic radius for size, which is just half the diameter. And that's from the center of the nucleus to the outermost electron orbital. So let's go back and think about this again. Hydrogen or helium, which is bigger? So once again, look at your periodic table and make a decision. What did you say? Some of you say hydrogen. Maybe some of you said helium. Maybe some of you said, hey, Miss Backus, I knew there was a trick to this question. They're the same size. They both have electrons in the 1s orbital. The 1s orbital is its outermost orbital, so they must be the same size. Well, let's draw it and find out. I have 1 proton here and 2 protons here, 1 in hydrogen, 1 in helium. I also have 2 neutrons, so that's my nucleus. And you are right, they have electrons in the 1s orbital. Okay, so this would be the 1s orbital and the 1s orbital. And I've got 1 electron here, and I've got 2 electrons here. And so that makes logical sense. This should be the same size as this. But guess what? That's not true either. So what is the answer? Well, it is based on this 1s orbital, which is the outermost orbital. But the problem is this 1s orbital is being pulled into the center by a positive 1 charge. This 1s orbital is being pulled into the center by a positive 2 charge. So what's happening is this orbital gets pulled in tighter than this orbital, and this then is the smaller atom. So if I drew it again, it's actually smaller. It has 2 protons and 2 neutrons, and the 1s orbital is smaller because it's being pulled in by more protons. This is a bigger nuclear charge, so it is a smaller atom. This also goes back to the last unit when we talked about emission spectra or line spectra and how every element had a different line spectra. And that's because even though electrons are in the same orbital, the 1s orbital for hydrogen is different than the 1s orbital for helium because hydrogen only has 1 proton in its nucleus and helium has 2 protons in its nucleus. So maybe you got that right, maybe you got it right for the wrong reason, or maybe you got it right for the right reason, but hydrogen is bigger than helium in diameter. Not in mass, but in diameter. So let's try that again, see if you can figure this out. Which is bigger? Let's just take the next element. So which is bigger this time? Helium or lithium? So take a look at your periodic table. How many people said helium? How many people said lithium? Well, let's go ahead and draw them again. I have 2 protons and 2 neutrons, and then I have 2 electrons in the 1s orbital. Okay, so that's helium. Lithium, on the other hand, has 3 protons, and it has a mass of about 7, so I'm going to say it has 4 neutrons. That's in the nucleus. And it has 2 electrons in the 1s orbital. And if you're thinking, wow, this 1s orbital is probably a little bit smaller than this because it's being pulled in, which is true, so that's a little smaller. But this is not where it stops. It also has one electron in the 2s orbital. So now, which is bigger? The helium or lithium? Well, if you guessed lithium right, you are correct. And why is that? Because the diameter contains a 2s orbital, which is bigger than this 1s orbital. Now let's add one more piece of information that we're going to use later on. See this one electron here? You might think this 2s orbital is being pulled in a lot, just like this 1s orbital is being pulled in, okay, by 3 protons. You might think this 2s orbital is being pulled in because it also is being pulled in by 3 protons. But that's not totally true. This electron in the 2s orbital is being pulled in by 3 protons, but also there are 2 electrons kind of blocking the path. So it's being pulled in by 3 protons, but there's 2 electrons in this 1s orbital between the 2s orbital and the nucleus. So they're blocking the path. They're blocking the attractive forces of the nucleus. So 3 are pulling in, and 2 are pushing back out again. It's kind of blocking the charge of the nucleus. So it's about 1-ish charge pulling in. And we're going to talk more about this in detail later, and that's going to be an effective nuclear charge, which is how many protons are pulling the electron towards the nucleus, and then also takes into account how many electrons are blocking the path between the outer electron and the nucleus. And that's called shielding. So we're going to have a whole separate video on effective nuclear charge, but that will come in later. So which is bigger? Lithium is bigger. It's got this 2s orbital in addition to the 1s orbital. All right. Now, next question. Maybe you're getting the pattern. Lithium or beryllium? Find them on the periodic table. Which is bigger? Okay. So I have lithium, which has 3 protons and 4 neutrons. Beryllium has 4 protons, and let's say it has a mass of 9, so 5 neutrons. This has 2 electrons in the 1s orbital, so there's 2 electrons here. And there's 1 electron in the 2s orbital, so this is the 2s orbital, so 1 electron out here. So the diameter is from here to here. So this has the 1s orbital here, 2 electrons in here, and it also has 2 electrons in the 2s orbital here. So I didn't draw these very well, but you might think, well, maybe these are the same size. Oh, no, you're not going to fool me again, Miss Backus. They both have the 2s orbital, okay? But this is being pulled in by 3 protons, blocked by 2. This is being pulled in by 4 protons, still blocked by these 2 electrons in the 1s orbital. Still, this is being pulled in by more. So this 2s orbital gets pulled in more than this 2s orbital, so the beryllium is smaller. And this one is bigger. 3 protons pulling in, 2 protons kind of blocking the path. Here we have 4 protons pulling in and 2 protons blocking the path. So a larger charge inward, a larger nuclear charge or effective nuclear charge. This gets smaller. And so lithium is bigger than beryllium. What about beryllium and boron? This is also very tricky. What about beryllium and boron? So I'll give you a second. Make a decision. Think about the size of the outer orbital. Okay. And here we have it. So beryllium had 4 protons and 5 neutrons in the nucleus. I don't think I drew the circle around the nucleus last time. And boron has 5 protons and 5 neutrons in the nucleus. Then it has 2 electrons in the 1s orbital. And then it has 2 electrons in the 2s orbital. Boron has 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, and now we've come to 2p orbitals, and we have a drawing problem. Okay, so sometimes you might see the textbooks revert back to Bohr here to draw these, but I have the 2p orbital, but the 2p orbital is still in the second energy level. It is not significantly bigger than the 2s orbital, but it's got all these crazy shapes to it, right? But it is not bigger than the 2s orbital. Okay, so it's about the same size. Not exactly, but it's similar in size to the 2s orbital. It's different in shape, but similar in size because they're both second energy level. So now I have to think, okay, which is bigger? Well, once again, these electrons are being pulled in by 4 protons, being pushed out by 2 electrons. This is being pulled in by 5 protons, being pushed out by 2 electrons. Therefore, this is being pulled in more. This is smaller. And this is bigger. Now, I hate to go back to Bohr, but sometimes it's a little bit easier to see than this. So just for now, we're going to draw a little Bohr atoms, all right? So we have beryllium and we have boron, okay? It's a little bit easier to draw, but we know it's not exact. So we have 4 protons and 5 neutrons for beryllium, and we have 5 protons and 5 neutrons for boron. Then if we drew Bohr, I would have 2 electrons in the first energy level. See, I almost said 1s because I'm used to the modern view. And then 2 electrons in here, okay? And then for boron, I'd have 2 electrons here. And I would have 3 electrons in the second energy level. So once again, these are being pulled in by a force of 4. These are being pulled in by so this is being pulled in by a force of 5 protons. But remember, these here in this inner circle, the first energy level, okay, are kind of blocking the path to the nucleus. So it's kind of being pushed out by 2 but pulled in by 5. This is being blocked by 2 but pulled in by 4. So still the net pull is bigger on this. So once again, this gets pulled in a little bit more and this becomes smaller and this is the bigger. So let's kind of summarize what happens, okay, using our periodic table, okay? So as we go across the periodic table, we are in the same or lower energy level, same energy level, except for the D's are 1 energy level lower. So we keep adding protons, making the nucleus pull in more and more and more. So as I go across this way, the atoms get smaller and smaller and smaller, okay? But when I go down this way, they get bigger because I go from the 1s to the 2s to the 2p. Oh, sorry, try that again. The 1s to the 2s to the 3s to the 4s to the 5s. Each time an extra energy level, bigger, bigger, bigger radius, bigger, bigger diameter. But as we go this way, I'm just filling in the second energy level. Protons are getting more and more. The nuclear charge is getting bigger and bigger. The orbital gets pulled in more and more and more. It's kind of like gravity pulling them in. Here, once again, if I go this way, the nucleus is getting stronger and stronger and stronger, pulling it in and in, it's getting smaller. But when I jump down to the next row, I get to add an extra energy level further away. So it gets bigger, then it gets smaller. It gets bigger, then it gets smaller. So as we go from left to right, the atoms get smaller. But as we go from top to bottom, they get bigger. So let's take a look at one of those charts. So if you went online to webelements.com, so go there online, you'd see a chart like this. And so you can click on the different elements and it will show you the size. And some of them you can hardly see, they're just little tiny points. But as you see, as we go this way, they get smaller and smaller they get smaller and smaller until they're almost too small to see. But as we go down this way, we keep adding an energy level. This is the 1s, the 2s, the 3s, the 4s, the 5s, the 6s. So as we go down this way, they get bigger, but as we go across, which is anti-intuitive kind of, as we go this way, they get smaller. Why? Because the effective nuclear charge gets bigger and bigger and bigger as we go that way. All right? So that's what we have, atomic size and the periodic table. If you look carefully, there are some exceptions to the rules, but we're not going to look at that closely for this video. So there you have it. I hope you enjoyed today's lesson.